All right, good afternoon and welcome to ECE 164 discussion section. Couple of things that I'd like to talk about today in terms of announcements. Let's start with homework 4. So one of the comments that I got from the TAs in particular was that a lot of students struggled with problem 4, in particular, these two subparts, so part D and part E. The issue is really coming down to doing ZVTCs and writing out the time constants for this particular circuit. And it wasn't one single issue. There were several issues that students seemed to struggle. I'm happy to go through and do this problem if you guys would like, if somebody wants to chime up and say yes. Otherwise, I would encourage you to look at the solutions and make sure that you really understand how to do ZVTCs. In particular, some of the ones that are a little problematic are this C diode. When you're looking into this source of this transistor, you can't just write out the expression for it. If you ever have questions about finding the impedance that you see at a particular node, you can never go wrong applying a test voltage or a test current and finding the corresponding value. I will say a lot of the times you can just write out exactly what the expression is without a lot of math, but don't be afraid to write them out if you can't directly see what the impedance is, or if you just want to check the impedance. So I guess I'll pause for just 1 second. Does anybody want to see how to do this problem, or you just want to look at the solutions?
Could you show us, please, Professor?
Sure. All right, so do you have a preference of part D or part E? Let's start with D just because it's first. All right, so the first thing that we're asked to do is we're asked to find the 3 dB bandwidth with ZVTCs. Okay, so we need to draw the small signal equivalent of the circuit. So RG in this case, for part D at least, is 0. So at the gate, we have grounded. The source, we're going to have R diode. And we're going to have C diode. At the drain, we're going to have R1. And CL. All right, so a couple of things that I've done. All of the independent voltage sources have been shorted. So things like VDD got shorted. Independent current sources got open. So you'll notice that I-bias is an open circuit in this. And let me make sure if we're supposed to include neglect R out, the body effect, and all device capacitors other than CGS and CGD. Okay, so we do need to include them.
Professor, this might be a strange request, but could you change the type of like line that you're doing? It seems like it's almost like a paintbrush stroke or something, and some of the letters come out kind of hard to see. I don't know if that makes sense.
It does. I wish I could. This is the Zoom default.
Gotcha. Okay, no worries.
It makes my already bad handwriting worse. I'll try to write as neatly as I can. Is there any one in particular that you're having a hard time seeing though?
No, I think I get the general idea. I just yeah, I understand what you're saying though. It's kind of a pain working with these sometimes.
Yeah, the Zoom doesn't have quite the same settings that a lot of the other things do, like PowerPoint or anything else. All right, so ZBTCs, what we need to do is we need to go through this and we have to pick one capacitance at a time. And we're going to then solve for the impedance that we see at each of those nodes, okay? So some of them are pretty easy and other ones are going to take a little bit of work. So in particular, this CGS and this C diode, these two elements are in parallel. So they don't look like it from the drawing, but one node is connected to VS, the other node is connected to ground. We could lump these together into one capacitance. The same is also true of CGD and CL. They're connected to ground and they're connected to the drain node. And so really we only have to do two time constants. Okay. Everybody see those two?
Yes.
Okay. Now the next question is, can we just eyeball this? Can we simply write out without having to derive any expressions and figure out what the time constants are? And the answer is no. For all of these cases, the fact that we have this R diode down here, it's going to complicate our KCL and KVL expressions. And we can't just directly identify what the driving impedance is. So we're going to need to write out KCL, KVL. So I'll go ahead and set these up. And then I'll leave some of the solving to you, unless you guys really want to see it, because I'd like to show a few other things. Does that sound all right? All right, so if we wanted to solve for this first capacitance, okay, we essentially need to do KCL at this node. Okay. And so we would write out our system of equations as 1 over R diode, Vs, that's the current that's leaving here, plus negative GM VGS, that's the current that's coming down here. Okay. And we're going to set this equal to 0. Okay. VG in this case is equal to 0. And so we can directly calculate what VS is. Oh, excuse me, I forgot to put in a test source. So I'm going to put in, let's see, what do I want to put? I'm going to put in a test voltage here. So why did I pick a test voltage? I picked a test voltage because if we know VS, it's very easy to calculate the rest of the expression. So I need to account for the current that's coming out of here. And so I'm going to have I test plus 1 over R diode minus GM VGS. And so then I will solve this for effectively VS over IT. That's going to be equal to the driving impedance. From that, I will get that the time constant is equal to R times the sum of CGS plus C diode. All right, so that's this first time constant. Any questions about that one?
Are you indicating R as R diode? I'm assuming. I'm a little lagging behind, so that might be.
Sorry,
You might have already
what was-
explained it.
what was the
What is
question?
R?
R is VS over IT.
I mean, are
So
you implying that
we're
R is
going to
equal to R
solve,
diode?
we're going to solve this equation,
Yeah.
and VS divided by IT from this expression, that's our driving impedance. And
Yes.
so our time constant is R times the total capacitance, which is CGS plus C diode.
I mean, like, is R equal to R diode, or you're just saying that this is how you
No,
would
R is not equal to R diode.
Okay, it's just like a general sort of a conclusion.
Yeah.
Because R, like, I mean, R is not on this. You're just sort of showing us the steps. It's not actually like the solution, right?
Yeah, exactly. The solution,
Okay,
the
okay.
solutions are
Got it.
online, and I'm happy to
Yeah.
solve it. It's just in the
Yeah.
interest of time, I feel like I should set this up, and if there's questions about the setup, that's where most of the students had problems just writing out, even getting to this step, not solving the expression. I think that you guys can solve this expression.
Gotcha. Okay, thank you.
All right, so if we now do the other capacitance, so we're going to do this in a very similar fashion. And remember that anytime I'm looking at the capacitance, I'm going to remove the other capacitance. So I'll take them away. So now we're going to do KCL at this node. And I'm going to put in a test current for no reason other than just to do it differently than I did the first one. So KCL at the drain. I will have minus IT plus VD divided by R1 plus GM VGS is equal to 0. So the current that's flowing out of my test current source flows into this resistor, and the current that flows here. I'm also going to need to write an equation at the source node. So at VS, I will have that VS divided by R diode plus negative GM VGS is equal to 0. Okay. All right, so I'm going to solve these two expressions. Again, solving for VD divided by IT. And that's going to give me the driving impedance. And then my time constant will be equal to CL plus CGD times R. Any questions about that? Does everybody understand? I guess the most obvious choice is just to say that the impedance is R1, but it's not, or RL rather. It's not just RL. Does everybody understand why it's not just RL?
Is it because some of the current flows through our diode as well?
Well, actually, I shouldn't say that. It could just be RL. We need to solve this to prove to ourselves whether or not it is RL. But yes, essentially, we could be siphoning off some of the current into the transistor itself. We won't know until we solve this set of equations. I guess my point is that it could be just RL, but it's not immediately obvious from the schematic. We actually need to solve this out to prove it, what the driving impedance is.
So if we were to solve all four capacitors separately, because they're in parallel, we should expect to get the same answers for, like, we should just essentially just get two answers.
Yes.
Okay.
Yes. If you did not realize for whatever reason that CL and CGD were in parallel and you left them separate, you would simply end up with the same expression again. So you would find the same driving impedance for CL and CGD, but it wouldn't do any harm.
I have a question, Professor. about just the value of CGD, because we know that it's equal to COV using the equations in one of the previous lecture.
Mhm.
But COV has units of femtofarad per micrometer.
Uh-huh.
So, but like the units of a capacitance of a capacitor is in farads, not farads per micrometer.
Yes, everything that you said is correct. So there's two capacitances here. And let me draw a transistor to kind of help us with this. Let's make this a PMOS. It doesn't make any difference. All right, so your question is that I gave you that the oxide capacitance was something, I don't remember the exact number, 15 femtofarad per micron squared, and that the overlap capacitance was 1.5 microfarad per micron. And your question, very astutely, is that these aren't capacitances. They're actually normalized capacitances to the area, okay? And so if you think about this as a 3D structure, which of course it is, the overlap capacitance really depends on how wide the transistor is, right? So in this dimension, I pick up overlap capacitance from how deep this transistor, how wide this transistor is. And so CGD is equal to the overlap capacitance times the width of the device. The CGS, or the total gate capacitance, I'm just going to call this gate because it's not quite CGS, is going to equal to Cox times W times L. That is, this is just a parallel plate capacitor, a two-dimensional parallel plate capacitor, due to the area of the transistor. But the key to remember is that the overlap capacitance here does not depend on the length. It only depends on the width. The gate capacitance depends on the total area of the device, W times L. Does that make sense?
Right, but for CGS, I use the other equation, the 2/3 WL COX plus C overlap.
Yes, that's why I didn't write it out, but yes, that's exactly the right equation.
So that COV again is just multiplied times the width?
Yes, so CGS is equal to 2/3 WL COX plus COV times, or COL times W.
Okay. Thank you.
Because we have the portion of the gate capacitance, or the oxide capacitance here, and we have the overlap capacitance on the source side, which again depends on the width of the device, not the length of the device.
Is this always the case?
Mm-hmm.
Okay, because it just, I mean, I was just confused because it wasn't written on the lecture slide.
Yep.
Okay.
Other questions? All right, I did want to spend 1 minute, not dwelling on it, but talking about the midterm, since we didn't get a chance to meet after the midterm. So how did you guys think that the midterm went, administrating it over Zoom? Were there any logistical or issues that were not conveyed? All right, so the one comment or one question that I did get quite a few questions about was, how will the final look relative to the midterm? The midterm is roughly 80 minutes, just over an hour and 20. The final, we're going to have 3 hours for the final exam. I won't make the final 2.5 times as long, given the time. The final will look extremely similar in format to the midterm. In terms of problem 1, we'll have true false questions where it's +1 if you get it wrong, -1 if you get it, +1 if you get it right, -1 if you get it wrong, and no points if you leave it blank. And then instead of 2 problems, there will likely be 4 problems for the rest of the exam. So I'm only going to make the exam roughly twice as long. So you should have plenty of time on the final. It will also be open notes like the midterm was. A lot of students afterwards told me in office hours and whatnot that they felt like they didn't have enough time. I think that in general, the time constraint usually comes if you don't know the material well enough to demonstrate it during the exam. You will have a little bit more time on the final, but really it's not something that you can spend 30 minutes looking through the lecture slides to try to find something to do that with. There were also quite a few questions about grades. Is there a chance to redeem if you didn't do well on the midterm? The answer is yes. I posted this on Piazza, but I'll also just repeat it for clarity here. I will compute your grade exactly as it's listed in the syllabus. And after that, I will go through and I will look for any outliers. Outliers where, on the final you scored proportionally higher or significantly higher than your peer group that would otherwise get the same grade. I do find these occasionally, and I will bump them up, or move them to an appropriate place that positions their final with the rest of their peer group. This happens every year. Most of the time, it's the difference between C and a C+, or C and a B-, or a B- and a B. It usually is not the difference between a D and an A. In fact, I've never had a D go to an A. I have had students that went from, I think one of the biggest ones was like a C+ to an A- or something to that effect. The final is comprehensive though, and the final is exhaustive. It covers all of the material. It's hard. I think that you guys should have seen probably from the midterm. The midterm is going to ask you questions to demonstrate that you understand and can show me that you know how to do this material, but it's not going to use the exact same problems that you've seen before on the homeworks. If you do the homeworks, the problems and the techniques are very similar, but it's not the exact same problem with all of the numbers multiplied by 2 or something silly like that. But I did want to open it up and find out if there were any questions about the midterm or exam logistics going forward. All right. So I do have a little bit of a demonstration that I would like to show today. But are there any questions about the lecture slides before we get to that? You guys have had a lot of slides now.
I just had one question.
Yeah.
So will the circuit given in the project be discussed in the class in the amplifier part, or?
Yeah, so the closest that you're going to get is parts of lecture 10.
Okay.
So in lecture 10, we do kind of this entire analysis of a, where's the best starting point? Of a single-ended OTA. The techniques of how to go through this analysis for like the DC biasing, for the small signal, calculating the differential mode gain, and the common mode gain. You should use this to leverage off of it. And then And then essentially this, right? So
Yes.
this, because what we're doing on the project is a two-stage amplifier. The second stage actually looks a lot like exactly what's drawn here. The first stage is a little bit more complicated than this in the sense that R1 is not just a resistor. This GM1 is actually very easy to calculate. It is the same GM as a folded cascode. It's the output impedance that's a little bit more complicated, and there are going to be additional poles that can affect both your phase margin and whatnot. The TAs actually didn't want me to give you all of these equations because I didn't give them to students in previous years, and they thought I was being too generous and too nice and that I was giving you guys too much information, but I felt that it would be helpful. But if you do have questions, make sure that you really kind of study lecture 10. It's a long lecture and it covers a lot of material, but it really does set you up with almost everything that you need for the project.
Yes.
And
I was
this
just
one- oh, go ahead. Sorry, Samir.
no, I was just thanking. I was just confused because of the folded circuit part, but I see that it is also available. So yeah.
Yeah, so the folded cascode is here. I'm not going to go through the detailed calculations for this. I do leave that up to you guys to think through how to do it. I talked about this quite a bit, and I can give you guys some more hints if you have a few more questions about it, but I'm not going to do any more detailed calculations on this.
Yes, that's all right. That will be on us. That's all right. Thanks.
Elizabeth, did you have a question too?
I actually think it was, yeah, about the telescopic amp. So I'll wait now.
Here it is.
Yeah. And this is about yeah, I mean, I feel like in general too, I probably might have some general project questions, but definitely save those to the end. So I'll let you get through.
Sure. So I did make one update to lecture 10. Slide 10 in particular, I've posted the updated slides. I'm probably not going to re-record the lecture, so I will just tell you here. In calculating the maximum input common mode of this circuit, due to the asymmetry in the load, there's a different solution depending on which side of the branch you calculate. And so what I've done is I've added the other side, 1 and 2, and it's going to be limited by the minimum of these two. And so it turns out that it is actually the second branch that limits it. And so it adds a VTP term into this expression. So there is a small update here if you want to re-download the slides for that. All right, one other quick discussion about the project. At this point, I would hope that everybody has a partner. If you don't have a partner, I would very strongly encourage you to post on Piazza and try to get a partner. Please remember, though, that it is only teams of 2. I've had many people post and ask if they can be with their already existing team of 2 to make it a team of 3. The answer is always no. Projects will be either alone or in teams of 2. There's no other teams. A lot of these specs should now make sense based on what you've seen from lecture 10. And the biggest hint that I can give for analyzing the circuit is, the following advice. How do you eat an elephant? Does anybody know this?
You cut them in pieces?
Yeah,
You don't?
one bite at a time, right? So don't try to write out KCL and KVL for 42 nodes in this circuit. Break this thing down into small pieces, manageable bite-sized chunks that we can take on, right? And so when I say that, what I really mean is that, we've talked about this. This is a folded cascode amplifier. We know how to analyze that. This is a common source amplifier. We know how to analyze that. This is a constant GM. We designed one in homework 4. This part is all about biasing. And so break this down, and almost always I would work from the output back in, okay? Start with the signal path and work back to the biasing. When you're analyzing circuits, you usually will go this direction. We'll start with the DC biasing, find all of the operating point, and then do small signal and work backwards. In doing design, you want to start at the output. It's the only thing that you really know. We know about the load capacitance. We don't know much else. And go this other direction. We're going to start with a small signal model. You're going to linearize this circuit. You're going to build an equivalent circuit that looks a lot like the one that I showed you on slide 10. Okay. And so there's some design choices that you will need to make. You know, the simplest of which is 1. There's 2 gain stages here. There's AV1 and there's AV2. Okay. And you have a spec of 70 dB. Okay. So the first thing, or one of the first things that you need to do when you're designing this circuit is think about how you're going to partition the gain. How much gain do you want to get from the first stage versus how much gain do you want to get from the second stage? Okay. And part of the reason that I have you do a lot of homework problems, design problems in this class is 1, to get you familiar with the technology, 2, to get you familiar with cadence, but 3, to kind of give you a sense of what's possible, right? And so, you know, a simple thought experiment, you might think that it's a good idea to get 65 dB from this and 5 dB from the second stage, okay? Alternatively, maybe you only want to get 5 dB here and 65 dB from the output stage. Okay? I can tell you that one of these is definitely not possible. Okay? It would be really hard to get 65 dB from the second stage. The entire reason that we're using a folded cascode is that we build a very large R out at this stage. So we should be trying to push a lot of the gain to this first stage. Okay. Once we've kind of partitioned the gain between AV1 and AV2, then we need to start thinking about frequency planning. Okay. On your axis, on the S-plane, where are you going to position the poles? And what are you going to do with the 0? So nominally, we have a right half plane 0, which is terrible for our phase margin. And so we have a couple of options that I talked about in lecture 10. One, we could push it out to infinity and move it back here. We could try to cancel one of our non-dominant poles. But you really should start thinking and planning out where you're going to try to position these poles. And some of them, you know, the non-dominant poles in particular, they're not really, you're not going to design to set them in a particular place. They're more or less going to end up at a particular place. But this dominant pole, you will absolutely position it. You will size parts of this circuit and components in order to precisely put that where you want it. All right, and I'm going to go through an example of how to do this for a different type of a circuit, but a large circuit in just a second. Are there any other questions about the project before I go to that? I guess first and foremost, does everybody understand all of these specs? I mean, every one of these should mean something to us now. Perfect. All right. All right, so what I want to do today is talk about a design example and how we can walk through a slightly more complicated example than some of the simpler examples that I've done. So previously I did this for a common source amplifier. You'll recall that we first designed the architecture. We selected an architecture, we did some analysis, and then we went through and started identifying the kind of design knobs. We're going to do the exact same thing today here, but we're going to do it for a larger circuit to get a sense of how to deal with complexity. All right, so here's a circuit that I showed you in lecture 9. This is a multi-stage, or excuse, lecture 8. It's a multi-stage amplifier, and we talked about kind of the various different stages of it. So we've already analyzed this circuit. You know, very quickly, just to reiterate this, we have the stage over here. This is the this is our bias. Okay. This is a common gate amplifier. Then we have a common source amplifier to get some gain. And then we have a common drain amplifier to have low output impedance in order to drive this load. Okay. And so we computed the gain as the transfer function first from here to this node. This gets reflected back into a voltage through this resistance. The voltage is then amplified by the gain of the second stage, which we're calling GM RCS. And then at the output, we have an attenuator that's from this common drain stage. Okay, so again, current copied at the input, reflected into a voltage through RCG. That's why we have this RCG term in the gain expression. Then we have a common source second stage, and then we have the output stage. Okay. So a couple of things now. If we wanted to design this, I've made up some specifications. I want to have a gain of 20 kiloohms, bandwidth of 30 megahertz, input capacitance of half a picofarad, load capacitance of 1 picofarad, and my objective is again to minimize power. Okay. So very similar to what you are going to try to do in your project, albeit with a slightly different circuit. Okay, so the first thing that I'm going to do is I'm going to look at the capacitances that are in this circuit. What I'm trying to do here is identify and position all of the poles. Okay, so at the input, I'm going to have some capacitance from this transistor M1. I'm also going to have the input capacitance from this input source that's given to me as Cin. And then I'm going to start to make some assumptions. Okay. Again, the idea with my first cut design is not that it's perfect. I want it to be, call it 10% of the design target. And so I'm going to make simplifications like CSB relative to CGS. I know that that's on the order of 10 to 15%. And furthermore, when you couple that with a large Cin fixed capacitance, the CSB is fairly small. Okay, and so it's a fairly safe bet to neglect that in my first pass calculations. Then I'm going to go through and kind of lump all of the other capacitances that I see at various different nodes. And again, you'll see that I'm going to, given the fixed output capacitance that I already know, I'm going to neglect CSB in my first pass design analysis. I will keep things around at other points for a little bit until I know their relative capacitance. But since I'm given a CL and given a Cin, I think that it's reasonable to make some assumptions about CSB1 and CSB3. All right, so now in this particular circuit, I've gone through and I've done the time constant analysis, and I found all of the time constants. Okay, so I did the time constant at the input, the time constant at the second stage, time constant for CI3. There's a CGD2 that's Miller multiplied in the previous slide. So this capacitance right here. And so we're using Miller's theorem in order to calculate the effect of this time constant. And one of the important things is as I go through this analysis, I should start to look for terms that I recognize. You know, GM2, RCG, RCS, if I go back just a few slides, we said that this was our gain, right? Our gain was the gain of the second stage times RCG times this, you know, unity gain or slightly less than unity gain source follower output stage. And so I want to start to distill these time constants down to get them into simplified expressions. Okay. Same thing when we go through and we calculate the time constant for CGS3. Okay, so this output time constant right here. If you go through all of the math, you'll find out that it depends on ratio of GM to GMB. We have an expression that we've derived for GM to GMB. We know that that's on the order of about 10 to 20%. Okay? And so what that lets me do is I can simplify this to GM3 divided by GMB3 as being approximately 5. Okay, and I can start to simplify down these expressions. Okay? So the point is here, I don't want to be stuck with very high entropy expressions when I'm trying to come up with design equations. I'm willing to sacrifice a little bit on my accuracy in order to have simple design expressions that I can quickly calculate and understand what the big drivers are in the performance of the circuit. All right, so once I have all of the time constants, I can use them to estimate the total bandwidth, okay, by summing up each of these time constants. And you know, even after making some of these simplifications, things like taking this and turning it into the gain, simplifying GM3 divided by GMB3, simplifying GM3 plus GMB3, I'm still left with a pretty messy expression. Something that I still need to simplify further, okay? And so what I've done is I've gone through and I've characterized the ratios of capacitances for this particular technology. These are very particular technology numbers. You need to do this for each type of technology, but they're pretty good estimates once we have a handle on them. And so things that I want to look at are ratios of capacitances for the same transistor. So for example, if I have CDB divided by CGS, I know that this is about 0.3 in our technology or in my made up technology. CGD divided by CGS is about 0.25. GMB divided by GM, I've already talked about this one, it's about 0.2. Okay, so I'll show you the actual numbers that I did in my appendix in just a second. Then what I can do is I can go through and I can continue to kind of simplify this by getting ratios. Okay, and so the important thing is to identify key drivers for each of these time constants that I can use as my design variables. Okay, and so you can see what I've done here is just simplifying this by using those ratios that I described on the previous slide and kind of getting things a little bit simpler that we have manageable knobs and we can identify key design variables. All right, so my strategy in this circuit is to normalize the time constants to T total. Okay, and so what I've done is I've gone through and found, for example, tau1 divided by tau total. I'm going to call this my design variable 1. Okay, there's a lot of ways of picking design variables in circuits. This is just something that comes after practicing it and doing it a few times that you get a handle on this. Then the next question is, what do I want to budget? You know, in essence, what we're doing here is we're saying, I have a fixed bandwidth for this entire circuit. How much of that bandwidth do I want to give up for the time constant that's at the input? Okay? And partly this goes back to looking at our specs. So our spec at the input is that we have half a picofarad of capacitance. At the output, we have 1 picofarad of capacitance. both of these nodes are relatively low impedance in the sense that we're looking up into the source of M3 and into the source of M1. And so my initial guess is that I'm going to budget about 10% of the power for this particular, or 10% of the time constant for T1. Okay. CGS relative to Cin, again, I know Cin in the circuit, it's given to me. And so the question is, how much additional capacitance am I willing to add at this node? Okay. A reasonable starting point, in my opinion, is that we say that they're equal, that CGS and Cin are equal. That essentially means that we're going to have a fairly large transistor here that has low input impedance, i.e. it has high GM. Okay. Then I decide on the proportional of the time constant that I want to spend at the output. Again, it is also a low impedance node, very much like the first design variable. And so I initially budgeted about 10% of my 10% of this total budget there. Okay. And then, like your project, I need to partition the gain. Okay. So if we go back to the gain expression that we have here, the gain comes from really three places. The output stage, which has to be less than 1. Okay. We can ballpark that for right now at about 0.8. You know, we could push this up a little bit closer to 0.9 or 0.95. It starts to get expensive in terms of the amount of current or power that I have to pay to do that. And then at the input, we have some gain from RCG here. Okay. The trade-off with RCG is that if I try to make RCG too large, all of the capacitance at this node will limit the bandwidth. And so it's really, in my mind, this entire design problem boils down to this simple trade-off. It's how much gain can I get from RCG versus the time constant that I have at this node. And so by picking the gain of the second stage, and then as I was just describing, it really is about the second time constant, which is at the middle node here, T2A. This T2A is really how much capacitance I have here and how much ends up at the output. Okay. And so here, you know, we've budgeted about 10% of the total bandwidth, 10% of the total bandwidth. I'm actually estimating that a ton of the bandwidth comes from this second capacitance. Okay. So another way of saying this is that I'm assuming that the dominant time constant is really going to be split and it's going to be placed at this middle node. Okay. And then the last design variable is the ratio of these two capacitances, CGS3 to CGS2. Again, I think that a reasonable starting point is to say that they're roughly equal. Okay, so once I've identified these design variables, what this lets me do now is I can go through all of my calculations. Okay? I can go through and I can calculate all of the transconductances, I can calculate the drain currents, and then I can calculate the total power. Then I can look at M1, M2, M3, the three transistors that are the key transistors in this design, and look at kind of their ID and their FT. Okay? And what I'm looking at in this particular instance is if transistors are working much harder than others. And let me give you an example of what I mean by that. It could be that in order to meet my design objective of 20 kilo ohms of gain, that I put a lot of burden on the second stage. That is that I pick a lot of gain in AV2. That may force me to dump a bunch of current into M2 to get enough GM in order to have gain at the output. And this may turn out that my choice of putting gain at the second stage was too much or too little. The easiest way to figure that out is to look at how much current I'm dumping into a transistor and what its FT is. Both of these are metrics that we understand about how hard the transistor is working. Okay? And what I would do is I would manually, or if you were smarter, you would set up these in kind of an Excel or MATLAB or MathCAD script that you could then kind of adjust things to even it out. So for example, if I found out that I was dumping too much current into the second stage in order to get a gain of 10, maybe I reduce the gain to 5 and I put a little bit more of that gain into RCG. Okay? The trade-off certainly is going to be that as I have higher RCG, it's going to hurt my bandwidth. So it's going to hurt the time constants. And so I'll have to deal with that by playing with not just this time, not just this variable, but I'll have to balance out probably this variable as well in order to account for the lower gain that I have at that node. And really, it just turns out that this is kind of an iterative process, that your first design is very unlikely to be your final design, in the sense that when you want to optimize, you need to smooth things out and even out the effort of each of the transistors. And so you're going to find a reasonable compromise of partitioning the gain between the first and second stage, partitioning the bandwidth. And that's where having a script that you can even not automate, I'm not talking about even at this point automating it and doing like fmin search or anything, but just saying that I could go back in here and quickly change this to 5, and it recomputes all of these other parameters for me. Okay. The point here is that we should be doing the analysis and the quote unquote design by hand, and then we should go into SPICE. Okay, and so here what we're trying to do is we're trying to do some design optimization at a high level without getting too carried away with making the power to be the absolute minimum. Because if you recall, we made a lot of assumptions and we simplified things in our initial analysis. We took some of these things and said they're small relative to other impedances. We assumed that the ratio of GM to GMB was about 20%. All of these things, SPICE will do this. SPICE will accurately calculate this. It won't assume anything. Okay. And so what I want to do is I want to find a good, reasonable starting point for a design, simulate the circuit in SPICE, and then go back and look at discrepancies. Discrepancies between the GMs that I calculated and the GMs that SPICE simulates. And if they're within 10, 15%, I wouldn't worry too much more about that. 10, 15%, I can adjust these parameters to compensate for either under or over calculations. If it's 100% or 50%, that tells me that something is wrong in my calculations, that I didn't design something right, and I should go back in and fix one or multiple of my equations in order to account for that. All right, so now we have a working first pass design. What's our next step? That's where we can get into optimization, okay? And the advice that I will give you about the project is do not jump into optimization until you have this working by doing the above, okay? We have to be able to do hand calculations. You have to be able to identify the key variables in your circuit to meet the objectives. And we have to have some design variables. I mean, if you were to write out each and every design variable for this circuit or for your circuit, you could easily have 20 to 30 different variables. We have to distill them down to just a handful of key variables that we can then use to iterate on the design. And so the majority of your design should be on paper. Only at this last step do we simulate in SPICE and start to resolve some of these discrepancies. Any questions about this before I show you kind of the MathCAD optimization flow?
Just about the ratios. Sorry, go ahead.
No, you can go ahead. Go ahead.
Okay. I was just asking for the ratios that you took at the beginning for different capacitances. Can we do the same technique for our project, but like looking at the CMOS, like the technology that we have to use?
Yeah, you can definitely take ratios. your project is slightly different in the sense that, well, for one, I'm only trying to, let me go back to my specs. My specs only have a bandwidth.
Mm-hmm.
I'm trying to write, but it's not letting me write. Okay, believe me, it says F3dB is 30 megahertz.
Yes.
So we only have a bandwidth spec here. We don't have a phase margin spec or a gain margin spec. And so what that means is that I'm only doing a dominant pole in this design. I'm not actually that concerned with where the non-dominant poles are. They could all be stacked on top of each other and it wouldn't make any difference. In your project, we have to know where all of the poles are. And so the first hint that I'll give you is that we cannot use ZVTCs in your design. We have to know exactly where all of the poles are. So we're going to have to calculate KCL in order to find all of the poles and the non-dominant poles. But your question, can we take ratios if we see things like CDB divided by CGS? The answer is yes. And you should use these kinds of ratios to simplify things in your project as well.
Okay. Thank you for that.
Other questions?
My question is just in relation to spice. Like if I mean, if it's not something that's required for like our project, it might not be that big of a deal. But I did you give us any examples in how to simulate a spice, or I'm just not as familiar with that. But if it's not something that we have to do, then maybe it's not worth the little sidebar.
Simulate what in spice in particular? These values, these ratios?
I think so. You had it in one of your optimization strategies. You said like simulate the parameters in spice. What did it say? Yeah, simulating spice. I'm not entirely sure what you mean by that too, because you also have it in
This.
Yeah, simulate the whole circuit.
We're going to simulate the whole circuit, but you'll notice that even here, I could replace a lot of these with transistors, and I'm not doing it intentionally, right? So IB1, IB2, IB3, this IB1, these could all be transistors.
Yeah.
Even in this simple example, I'm leaving them as current sources. And so I would encourage you in your design as well, your first pass design, your first pass simulation should not be the first figure of the project with every single transistor. We should focus on things like the signal path. So you should do that common source amplifier. You should simulate the folded cascode. Only then would I start to go back in and dial in all of the biasing. Now, that's not to say that you shouldn't include transistors to do the biasing. So you'll notice here, in order to bias M2, I'm using what's called a replica bias, as you've probably seen 5 times on homework 5 already and are tired of hearing that phrase. The idea is that I'm using this transistor with a current source in order to generate the right bias voltage at this node. And so when you're biasing up the folded cascode, I would do the same thing. I would use one of the magic battery circuits that we've talked about in lecture 6 or 5. But instead of kind of mirroring around the currents like I do in the project, I would just put an ideal current source and be done with it.
And is that what you mean by like, because you had mentioned, I think, spice before as well, and you said not to, was it something about circuit monkeying or whatever, where you just kind of arbitrarily change values. You sort of had mentioned how you can do something in an optimized way, like through a spreadsheet, but not to use Excel. And I wasn't entirely sure what you meant by that, but if it's not something required and we can do it all by hand, then perhaps it's not, again, as important.
No, so a couple of comments. One, I actually think Excel is fine. The point being that you're going to do all of these calculations, and your first pass derivation or analysis of the circuit, you're going to get all these expressions. That's all fine to have and do by hand. As you come in and you've identified these design variables, you're going to want to play with them. You're going to want to figure out, roughly what is the power if I set T1 divided by T total as 10%, if I set CGS divided by CN as 1, and so on throughout the rest of this. You're going to want something that computes the power, it computes the bandwidth, it computes the gain. Basically, all of the metrics are being computed. You could certainly do this by hand, but my suggestion is I would have some kind of script. And I don't care if it's Excel, if it's MATLAB, if it's MathCAD, it makes zero difference, that does this computation for you so that you're not just plugging through all of these numbers for 5 hours.
Do you have an example of that, or you just mean like?
That's what I'm
Okay.
going to show you next. But
Okay,
before I
perfect.
get there, I want to make sure that we're clear on objectives, fundamentals, how we're going to do this. Any other questions before I go there? All right. All right, so here's my script that I use for this. And let me make the first caveat that I do use MathCAD for no reason other than it lets me write out the expressions in a very legible fashion. Left up to my own devices not to present to you, I probably would just use MATLAB because it's the most comfortable and easiest thing that I have handy. This takes a lot more time and effort for me to write out to get the expressions so that you can actually read them. But they come out a lot more readable than MATLAB scripts.
I believe MathCAD is not available on Macs, right?
No, I have to do this on my Windows PC. You're absolutely right.
Yeah. Also, like we'd have to use the VPN if we have Mac, and that's too much.
I know all these silver computers that we have don't run software anymore. All right, so what I've done here is I've put in some technology parameters, things like KN, KP, oxide capacitance, mobility, overlap capacitance, gamma, phi, VDD, things that we've characterized, over the course of the 5 homeworks. We have almost all of these parameters, okay? I've also put in a few other numbers in terms of the junction diodes relative to their coefficients. You may or may not need to do these. I would say for your project, it's probably not necessary to go to this extreme of calculating CSB and CDB for the transistors. Then I can show that we can calculate the FT of the transistor from the overdrive voltage and the length. This is just using the FT expression that I derived in class, depending on the mobility, overdrive voltage, as well as the overlap capacitance and the oxide capacitance. So just to show you some numbers, again, this is a slightly different technology than the one that we are using in 164 because this is published and I can't publish exact numbers for this technology. What this says is that if I have 200 millivolts of overdrive and a 1 micron channel length, I should expect an FT of about 780 megahertz. If I increase that overdrive voltage with the same channel length to 0.5 volt, I get a lot more FT. Okay. Same thing for a PMOS, 200 millivolts of overdrive at a 1 micron channel length, 390 megahertz. So again, one of the most obvious things that we see here is that there is definitely a discrepancy in terms of FT, right, between a PMOS and an NMOS. And so if I gave you the option to design this circuit from scratch, i.e. pick your own architecture, this is definitely something you would think about. Do I want my input stage, for example, to be N or P? And it would likely come down to this exact difference here. All right, then I can calculate some time constants from this, just looking at 1/2 pi times the the FT. And so I get transit frequencies or FTs for NMOS and PMOS. This is just to get me some kind of orientation on the technology. Then I have the function that calculates GMB relative to GM as a function of the source to body voltage, VSB. And so if I run this through kind of extreme cases, 2.5 volts, 1 volt, I see that it ranges from about 0.15 to 0.2. This is typical of almost every technology that I've ever worked in, where the ratio between GMB and GM is almost always on the order of about 0.2. Then I have some functions to calculate the overlap capacitance as a function of the channel length. Then I can normalize the overlap capacitance to CGS. And that's where I came up with this number. You can also simulate this from cadence to get an idea of what these capacitance ratios are. Doing the same thing for CDB relative to CGS. All right, so that's all just about the technology. Now we get into our actual design specifications. So I have the 3 dB bandwidth, the gain, the load capacitance that's given to me, the input capacitance that's given to me, and then some expressions to calculate what is the total time constant in this case. And I have a total budget of 5.3 nanoseconds that I can distribute to my various different design choices or design variables. All right, then I pick my channel lengths. In this particular design, I'm leaving these as kind of independent variables to start with. And then I go through my design choices that I calculated before, and I use my starting values. So 10% 1, 10% 10, and then 50% here. Lastly, 1 for the ratio of CGS2 to CGS3. So when I say that I have scripts, essentially it's that now I can use these parameters here in order to start to calculate things like the transconductance. So going back to the expressions that I have, I can massage them and get them in terms of my design variables. So I can calculate the transconductance of the first amplifier. I can calculate CGS of the second stage. I can calculate GM of the second stage. I can calculate GM of the third stage. Now that I have all of the GMs, I can calculate the total RCG that I need in order to meet the gain spec. I can calculate the resistor value of the second stage. And now I basically sized all of my transistors at this point. So I can go in and I can calculate the FT. Okay. And what I'm using the FT for here, again, is not that FT is particularly important in the circuit. I'm trying to get a sense of how hard these various transistors are working. Okay. And again, back here on the first page, we have a sense of what this technology is capable of. So for a 1 micron channel length with 200 millivolts of overdrive, I get about 800 megahertz. If I increase that to 500 millivolts, then I get about 2 gigahertz of FT. Okay, and keep in mind that our circuits can't really operate within a factor of about 20 to 50 of FT. And so looking at this, what do we see from these 3 transistors? Transistor 1 and 2, they're not quote unquote working very hard. What about this third transistor though? It's working pretty hard. Essentially what I'm having to do is I'm dumping a lot of GM in order to meet the bandwidth of this, right? And so if I think intuitively for a second, why is that the case? Well, it comes back to this, where is it? This design choice here, 3. The fact that I'm only giving the output time constant 10% of this total budget that I have in order to meet the bandwidth. Okay. In order to meet that constraint, it puts a lot of burden on this third transistor. Okay? And so if I was manually doing this, I would go back in and I would say, no, that was a bad choice. I'm actually going to give this, 20 or 30% and let it kind of compute and see how things fell out, in essence, to try to even out the FT of these three transistors. All right, once I have all of the sizes, now I can calculate the overdrive voltages for each of these. I can calculate the currents. I can calculate the total power. I can go through and calculate the width of all of the transistors. And at this point, I've basically entirely done the design on paper. And so I would go back and I would simulate this in order to make sure that it matched my calculations, that ID1, ID2, ID3 were all close to simulation values. Overdrive voltages were all very close. My total gain, my GMs, all of these more or less match my hand calculations. And if there are discrepancies, I need to track them down. And this is actually required in your report, is that you have to show me that you've matched your hand calculations to the simulation values and identify if there are differences, why. So why might, for example, VOV not be exactly what you calculated in simulation? What are a few reasons that that could be the case?
Doesn't it ultimately go back to like the fact that you've made a lot of assumptions? So not all of those assumptions are going to be true.
Yeah. What's the biggest one? What's the worst assumption that I've made?
No backgate effect.
Maybe. I mean, yeah. So I don't have the circuit here, unfortunately. Yeah. So in particular for GM3, for the third transistor, that could be a pretty significant error. The other thing is that I've assumed a square law model, right? When I did all of my calculations here, I assumed that GM was 2ID over VOV. Essentially, I haven't taken into account any short channel effects. And I picked longer channel lengths. So I picked 1 micron. It's less likely to hurt me at 1 micron. If I had picked the channel length at 0.18, I would probably see that there are going to be some pretty significant differences here, because the short channel effects are going to start to creep in. So if you are seeing quite a bit of difference and you can't really rationalize it, one way is to look at short channel effects to try to explain part of your discrepancies. All right, so at this point, I've essentially designed everything. I've identified everything. I would go simulate this, and I would see how close it came to meeting my design specs of 30 megahertz, 20 kiloohms gain. And if it didn't, if it was, let's say, 18 or 19 kiloohms, what knob would I change here to tweak to turn the gain up just a little bit? Same thing with increasing the bandwidth. And that's where designing this circuit and going through all of the hand calculations, it's really important to understand if the bandwidth comes up short, how do I increase it? If I have extra bandwidth, how do I reduce the bandwidth and save power? You need to know what these trade-offs are. There's too many knobs in the circuit that if you just go wildly trying to tune every one of them, you'll never figure it out. All right, so now at this point, let's pretend that my circuit is working and I want to take it to the next step, right? The next step would be automating this design. And so what I'm doing is I'm essentially taking all of the design variables as inputs to a function, okay? And this function is computing all of the parameters that I showed on the previous few pages. And then at the end, it's spitting out the power, okay? And so what this lets me do is this lets me explore the design space, okay? And so what I can show you here is, let's take this function P and give it all of the parameters, but I want to play with 2 of them. Okay, in particular, I want to show you what happens with how much gain I put in the second stage and this 5th design variable. And so the 5th design variable, if you recall, was how much capacitance I assumed would be divided between T2A and T2B. So it's the ratio of the time constants in the second stage. And so what is this plot showing us? This plot is showing us a couple of things. On this axis here is the gain, right? The z-axis is the power. And so if I try to put this up with a whole bunch of gain, and I try to move the time constant over here, you can see that we end up in this portion of the design where it takes a bunch of power. Basically, I'm shoving a whole bunch of current down M2 in order to make it have a lot of gain, but I'm also having to deal with the Miller multiplication of CGD. Okay. On the other hand, if I back off a little bit on the gain and come down here, you'll see that this is a pretty reasonable place in the design. And what's more important to me is that I don't have to solve this with a single value. There's not one best design in all of this. In fact, any space kind of in this purple region here is equally good in the sense that it just trades one thing for another, but it results in the end the same amount of power. And that's exactly what you're going to find in your project as well, and why I would expect that no two projects are exactly the same. Everybody is going to pick a different place on this Pareto curve and optimize for a different place. And so here again, this is the same curve. It's just I've rotated this 90 degrees so that you can see this a little bit better. This illustrates what I'd like to show you a little clearer, is that if you try to put too much gain in that second stage, you essentially just end up burning a whole bunch of power. Okay, and so this is a nice way to visualize kind of the trade-offs in the design. So for a gain between 6, 7, and 15, it's a very shallow design space. After I try to put too much gain in that stage, it starts to get exponential in terms of its expense, its power, that I have to pay to make that happen. All right, so any questions about how we did kind of this full design example? And I posted both the slides that I presented as well as this entire sheet online. I don't think that you can directly use a lot of this on your project. The intent is more just to get you insight into kind of thinking about how to do this type of analysis and this type of design flow rather than as a cookie cutter copy and paste. All right, well, good luck with your project, and I'll see you next week.